I'm Kristen. I am a core scientist here with the EPIC SEM team of Nuance. So I'm just going to give a quick little talk about our new Hitachi IM4000-II ion mill. This will probably be, whoops, oh no, what did I do? Let's go back there. Okay. A quick little talk just to introduce you to this new piece of equipment we got. Hopefully give you an idea of what it can do and why you might be interested in using it and if it might be a benefit to your experiments. So first, let's just briefly talk about what ion milling is. What is it exactly? Ion milling is a general term for sample prep methods involving removing material from a sample by bombarding the surface with ions, which leads to atoms being ejected from the sample in a process called sputtering. When ions hit a sample surface, they may scatter or become implanted in the surface, and they can also transfer their energy and momentum to the target particles, causing a sort of collision cascade. And if atoms at the surface get enough energy to overcome their binding energies, they can then escape. So ion milling can be done in a controlled way for a variety of purposes. And one purpose is to create a very smooth, flat surface for for imaging or for microanalysis. So an ion mill in particular is an instrument dedicated to making these smooth sample surfaces with minimal defects or artifacts, and usually refers to instruments that use a broad beam of argon ions. So it's often also called broad ion beam milling, or BIB or BIB. So that's pretty much the general idea here. An ion mill uses this broad beam of argon ions to sputter away at a surface until a smooth surface is left behind. Argon ions are used since they are inert, which limits the sample removal to purely physical sputtering with minimal to no implantation damage. Material that jets out has less surface binding energy, so it's more likely to be ejected through sputtering. So exposure to this broad ion beam will, over time, polish the surface until it's very smooth. So going to, yeah, smooth. Why is this important? Many imaging and microanalysis techniques rely on smooth surfaces, since surface roughness and deformations can obscure details and reduce measurement accuracy. So if you've taken an electron microscopy course here, or maybe an SEM training here at Nuance, you should be familiar with the concept of the interaction volume, where the primary beam of electrons will penetrate through a volume of material in your sample. And then various electron beam specimen interactions take place, giving rise to a variety of signals that then we use to build and analyze, build images and analyze our samples. So a worst case scenario is when you're imaging, you see scratches or cracks through your sample, maybe cracks right through regions of interest. But the more subtle roughnesses mean you get unpredictable changes to the yields of all these signals, which makes imaging and quantification more difficult, especially for the most surface-sensitive signals. So poorly prepared surfaces obscure layered structures, they distort interface boundaries in cross-section samples, and we'll look at some examples of that later. So a lot of reasons you might want to polish your samples. In particular, this is a big problem for EBSD samples. EBSD, or electron backscatter diffraction, is a technique to determine crystallographic orientation and microstructure in a sample. The primary beam of the SEM is focused on a tilted sample, and some of the electrons are diffracted off of the crystal planes in the sample's crystal lattice, and it forms these pretty patterns called Kikuchi patterns on a phosphor screen. The quality of these patterns decreases if those diffracted electrons have more opportunities to scatter in the sample before they leave the surface to be detected. therefore losing all that crystallographic information that you were interested in. So that's why a smooth surface is really important to getting good quality patterns for EBSD. And you can see here in this series of progressive polishing steps how it affects the quality of those EBSD patterns, how they improve as the surface quality improves. And here you can also see the improvement in mapping quality, where you get a lot of regions that are unindexed because the patterns were too poor, whereas now we have a full map. We have a lot of EBSD users here at Nuance, and so a lot of you are probably well aware of how important polishing is for getting good EBSD data, and you're probably very aware that this is not a trivial matter. It's a big bottleneck, I think, for a lot of you guys when you're trying to get EBSD data, where it could be very tricky to figure out the best way to get that good surface. So there's a lot of methods for preparing samples for either polishing or making cross-sections. So I'm just going to talk about a few of them here. They all have their pros and cons. Just to give you an idea of why you might want to consider moving away from some of these and maybe trying ion beam milling for either a final step or your first step. So cutting or slicing a sample with a razor blade is pretty crude, but it's easy, it's cheap. You probably have a razor blade sitting around somewhere. So sometimes when you want to make a cross-section sample, this is the first thing people try. And if you've ever tried to prepare a cross-section sample like this, you've probably found that it did not work very well. This is actually a kind of pretty good for a razor blade cut example, but what ends up happening usually is you crush and distort the layers in your sample, and you just don't see them very clearly. If you're very interested in thickness measurements, you'll probably find it's just not very accurate. It has very low reproducibility and minimal site specificity. So here you can see SEM images of a sample of thermal paper that was prepared either by cutting with a razor blade and then with subsequent ion milling, and you can see how much more easily you can distinguish the individual layers with the ion mill. Mechanical cleaving is also something that people do when they're preparing cross-section samples or to get a smooth break on a sample. It's another kind of quick and dirty method for sample prep. Here you can see a cleaved copper flip chip device that was done by cleaving. This sort of round copper bump was a little sort of further back, so it didn't get cleaved. But you could see here sort of the distortion in the shape. And you can also see that you lose a lot of this sort of fine structure detail. You just don't reveal it, really. Grinding and polishing is very, very popular, and for a lot of cases, it might be sufficient. It's great for processing large areas, but grinding can induce surface stresses, surface deformations. It can induce heating, plucking of grains, meaning sometimes individual grains might pop out of the sample while you're grinding or polishing. And so for surface sensitive techniques, you might find that conventional polishing methods don't quite work. Sometimes they might even leave behind a residue in the case of maybe using something like a colloidal silica. And all of this is going to hamper your results. And you can see here with this sample just how different using the ion mill reveals a lot more information and really helps to clean that sample surface. So this was a steel sample. If you've ever used an ultra microtome or a microtome, this is a popular method for especially TEM sample prep, sometimes SEM prep as well. Think of it like a deli slicer for microscopy samples, where a diamond knife is used to cut serial slices of a sample. The benefit of a microtome is that it doesn't really induce heating or ion beam damage, and you can get lots of slices of a sample to get a lot of information, maybe get a sense of 3D properties by doing this all in serial. For a TEM, it's also very good at making reproducibly thin sections, but it does suffer from a number of mechanical deformations. In blue, we can see evidence of crevasses that were formed by shear stresses. The yellow arrows you can see here, they're kind of pointing to marks left by the diamond knife itself. In red here, you can see these regions called chatter. Basically, as the diamond knife is cutting your sample, you get friction building up, and then it causes these periodic variations in section thickness, things that could potentially be cleaned up with something like an ion mill. So this leaves us with focused ion beam methods and broad ion beam methods. You may notice both have ion beam in the name. You might already be familiar with focused ion beam since Nuance is equipped with a plasma fib and very soon a new gallium fib. We also have a nano mill, which is another tabletop instrument. So you might be wondering how this compares with this new Hitachi ion mill. These are all ion milling instruments, but they work differently and they serve different purposes, which might be especially obvious between this focused ion beam instrument compared to these tabletop instruments just by the difference in their blueprints. On a fib, other applications are often available to be used in coordination with the ion milling. Things like secondary electron imaging, there's usually gas injection systems for deposition, micromanipulation, analytical capabilities like EDS and EBSD and others as well. At its most basic, the difference between them is in the name. A focused ion beam is a focused beam of ions, whereas this is a broad beam of ions. The nanomill also uses a focused beam, I think. So if we paint with a broad brush here, in a focused ion beam, you're dealing with much smaller spot sizes. We're in the nanometer regime because it's a converged beam. In a broad ion beam instrument, we're in the millimeter regime. It's very broad, near parallel. The currents are a lot lower with a focused ion beam, but a much higher current density, whereas it's the sort of flip in a broad ion beam instrument with higher currents overall, but lower current density. The accelerating voltages are usually around 30 kV in a SIB, but then you can also lower it so you can do cleaning steps. Our broad ion beam, the Hitachi ion mill, has a max kV of 6 kV. So the SIB has much higher lateral resolution. It's all about site specificity, whereas the broad ion beam is about large area processing. It's much faster milling rates over much larger areas. It's also gentler due to the low current density and the low energies. In a SIB, you may need to do a low kV cleaning step to remove or prevent damaged layers, and the nanomill fills a specific role of being able to do this very well at very low kV. It's still a focused beam, and it is rastered over the sample. So the Hitachi ion mill might be good for removing maybe broad overall surface defects, things like maybe curtaining effects, sometimes seen in TEM samples, but the nanomill will be better for that site specificity for thinning TEM sections and removing damage layers. So you can see a fib is great for TEM lift outs, atom probe prep, nanomachining, things like tomography, even 3D EBSD. It could also do cross sections, but with a much smaller area. For this broad ion beam instrument, this is mainly for polishing for EDS, WEDS, and EBSD, and maybe other techniques as well, things like AFM. It's good for damage and contamination removal, again, especially over large areas, and for making cross sections, large cross sections. So let's talk a little more about our Hitachi IM4000-II. This is a hybrid milling machine. So it does both cross-section milling and flat milling. Some ion mills in the market will only do one or the other. So that's a really nice thing about this ion mill is that it's very easy to switch between these two modes. Let's talk first about the cross-section milling and how that works. So basically, your broad beam of argon ions are going to hit your sample, that will also be protected by a mask so that you're only milling away this exposed region until you end up with a flat surface where then you can understand sort of what's going on below your sample surface and any layered structures. So you can see here in this animation, the broad ion beam going over the sample, where at the top here we have a mask and the sample is maybe sticking out a bit so that it starts milling where the beam is hitting the sample. We also have a swing angle of plus or minus about 30 degrees so that you can help get those artifact-free surfaces by sort of averaging over that area. You can also use shallower swing angles for deeper penetration depths. So doing cross-section ion milling with this instrument can get you about 500 micrometers per hour milling rates, maybe more. This was calculated on a silicon, so this will depend on your sample and the sputtering rate of the material that you're trying to make a cross-section of. And you can put in pretty large samples. These are the dimensions of the samples that can fit when you're doing your cross-section milling. So you can make cross-sections with a focused ion beam. You can see, again, this is much more focused, is the general idea. But a big difference here is just look at the difference in scale. 20 micrometers across here, 1700 micrometers across here. So it's just, it takes a lot longer in a fib to do something like this. There's also this mask here. You can do deposition in a fib as well. This image was probably taken it was taken at a tilted angle, whereas this is a actually perpendicular view. So that is cross-section milling. What do we mean by flat milling? This is the sort of true polishing method. The sample is tilted relative to the beam and can also be rotated to ensure that the material is removed uniformly. The highest current density of the beam is going to be at the center. So there's also an eccentricity that we can adjust to basically offset that high density region. So it's not going to sort of sit in the same spot as you're rotating. And so it'll spin around and around and really smooth out this nice large region. You can put in pucks and samples that are, about 50 millimeters wide, 25 millimeters tall. And the milling area is about 32 millimeters in max diameter. So flat ion milling at an oblique angle is what probably a lot of people are going to do, and this is what minimizes the dependence between the sputtering rate and crystal orientation of your sample, which will yield reduced surface topography and a flatter sample surface. It's also a slower sample removal, gentler removal. But we can adjust the tilt to more perpendicular angles to increase sputtering yields and to also enhance relief and topography between different grains. So we can see here with this sample before milling, we can see with the more oblique angles, they give a smoother finish, lower sample removal. The more perpendicular angles increase the sputtering yield, enhances relief. So we see that difference here where there's a lot more texture being shown. You can also see the difference in this top layer here that I think was a copper layer. So for analytical techniques like EDS or EBSD, you're going to be probably doing something like this to get that smooth mirror-like finish. So we're already finishing up here. Just to mention a few additional things about the Hitachi ion mill. There are also intermittent settings, basically an on-off setting for the beam between 1 second to about an hour. So it can be gentler for heat-sensitive samples. The beam's not sitting on it sort of continuously for as long. There's an auto shut-off feature, which is good for energy conservation if you need to walk away for a bit as well. There's a cross-section adapter holder. This is a special holder that's compatible with our Hitachi 3400 that allows for you to make your cross-section and then directly transfer it into the SEM without having to sort of remove it and remount it. Some possible future upgrades that some of you might be interested in knowing can exist. There is a cryo temp control unit for heat sensitive samples, a liquid nitrogen cooling unit that can go down to negative 100 degrees C. We can also potentially acquire an air protection unit for air sensitive samples. So if these are things that you think would be extremely helpful for you, something you might need for your work, definitely talk to us and we could talk about seeing what could be done about that. So that's pretty much the end. Lastly, I want to just mention to all of you Nuance users who are doing a lot of this analytical work with software like Aztec. We are very soon going to actually, if you want, we have access to a network license now. So if you want to be doing work sort of in the comfort of your own home, also come by our office and talk to us to see how we can get you set up so that you can work remotely with Aztec. So I'm going to finish up here. Thank you for coming. If you have any questions, let me know. And here is a QR code. If you are interested in Ion Mill training, it'll send you to our Nucor website and you can sign up for training with us.